I'm Suhyung Jang from Yonsei University, Seoul, Korea. I just received my PhD like early this year from my supervisor, Dr. Ghang, and today I'd like to share some like our recent findings regarding the potential of using large language model embeddings to train relatively smaller AI models so they can comprehend like building semantics there. So the figure here is showing what's called the semantic triangle, which is used in the field of semantics that explains how people communicate. So for example, like here, when we talk about an object that's referred as referent in the triangle, and the concept or the class that the object belongs to is referred to as reference, and the symbol, which is the terminology that we use to express those, really depends on which language you're using. And like nowadays, like it's not only important that we communicate, the experts communicate to each other. We are using AI models, and we want them to understand like what's going on, like in our industry, right? So in that case, the symbol changes from encoding from terminology, which means that the encoding is something that's like interpretable by machines. So there has been extensive research to enable AI models to interpret and also like associate the concepts to what they interpret in our domain as our domain object, which the examples include the image-based personal protective equipment detection, and also like element instance segmentation, as well as the graph-based these space classification based on graph-based representation of the BIM models. But the what is being less focused is like how do we like deliver this to the AI models. So for example, when we train AI models, we typically follow like conventional encoding method, which is like label encoding and one-hot encoding. And in label encoding's case, the label encoding just arbitrarily assign these integers to the classes that we want to classify, right? And then this arbitrary sequence is there, and that kind of distracts the AI models to understand like what's related to what. And in one-hot encoding's case, which all classes are equally distinct, it wouldn't have like those false similarity detection, but still, it wouldn't be able to reflect those similarities and differences between the classes. So I'm pretty sure like many of you already know what the text embedding is, and using text embedding, we're able to reflect those similarities and differences of the classes within the embedding. So for example, like here, you can see that these are the examples of the building elements, subtypes, and the types. What I mean by that is like walls and columns and those kind of like foundations. That would be like generic types, and when we get to specific types, like there will be like exterior walls or bathroom walls, and those kind of things will be subtypes. Then within the text embedding, those concepts will be placed close to each other if they have semantically similar context. So that was our motivation. So why don't we use this kind of semantically rich embedding to train smaller AI model so it can better represent those semantics? That's like how we started this research. So in typical AI model training, what we do is we put data into input layer, and there will be like multiple hidden layer or like any architecture of the specific model, and then we'll have output layer, which we compare the ground truth, which is from our training data, and compare like how different is the output from the ground truth. And then like we feed back to the model, and we iterate it until the return of the model, which is output, and the ground truth gets close enough, right? That's the training process. So what we did, what we made like two modifications into the training process. The first was dimensionality reduction, which we use Matryoshka representation learning to reduce the dimension of that high dimensional large language model embeddings into some dimension that's feasible to train relatively smaller AI models. And the second approach was we kind of like modify the, I mean like cosine embedding laws, that's something common, but we calculated the cosine distances between the embeddings. So rather than just make an AI model to decide like what's the category that's like being classified for the input, instead we aim the model to return something that looks like large language model embedding. So just to briefly introduce like what's the Matryoshka representative learning, what it basically does is it just like learns from one shot that what are the significant dimensions that's representing the semantics. So when we want to reduce the dimensions, you would reorder the dimensions from start to end, what's significant to not significant. So once we want to like reduce the dimension, we would just get rid of the dimensions at the back. That's like how it works. I mean, like it conceptually, but you can look into details. And then we use cosine embedding laws instead of like, for example, like in conventional multi-class classification test, we would use cross entropy laws, which it would decide like if the classified class would match what's in the training data set. But instead, what we did was we used cosine embedding laws. So we would make the model to return something that's like high dimensional, but not as much as like original, but still it will make certain dimension of vector that's very similar to original large language model embedding of the specific class. And to evaluate like if it's gonna work, we applied it on a task of classifying subtypes of building model, which includes 42 subtypes that's like managed by one of the major contractor in South Korea to manage their building projects that's done in BIM. And for a relatively smaller AI model, we use GraphSAGE, which is a graph neural network. And what it did was to parse the topological connections from the BIM model, and also based on their original element type, which I already mentioned, that's like walls and the foundation and columns. Then you would classify what are the subtypes that specific elements should be classified as. So to train and test the proposed method, we applied it on 5 build project, which we did kind of like cross validation. So training with four project and testing it on one, and we iterated like for all 5 projects. And we also tested like how the performance would differ based depending on like what embedding model we use and whether we compact the embedding or not. So we evaluate weighted average F1 scores to understand, because in this kind of like classification, the data is like skewed, and as I mentioned, we did like cross validation. So we weighted up and averaged the F1 scores for all 5 training and testing cases, and then we also analyzed statistical significance of performance differences between conventional encoding, which we use one-hot encoding, against LLM embedding, and then we also analyzed the differences of the performances when LLM embeddings are used, not compacted and also compacted. So the research shows that the utilizing LLM embedding consistently increase the performance compared to conventional one-hot encoding in all cases. But what we found out was that the compacted dimension ones work always better. I will explain it later. And when we did the statistical analysis, we only could find one case where the OpenAI text embedding 3 large compacted version was used, was identified as significant increase, but still the performance has increased slightly for all cases. And when we compare the performance of the compacted case and non-compacted case, it commonly showed that the compacted LLM embedding performed better compared to non-compacted LLM. But that doesn't mean that it's better to be shrunk, but it shows that we have to use right dimension of the compaction and also model architecture to get optimal performance. So to conclude, I think the contribution. I mean, like we are not at the contribution level yet, but I see many potential that we can use those semantics that's learned from large corporates and just apply them on a smaller scale AI model, which we always like want to do it because like we're always out of our domain data and it's really difficult to train our own model. But if we parse some like semantics from that and apply on a smaller model, which is cost like in resource wise cost effective, and it's faster to applicate. I mean, like the case I showed didn't really meet the time urgency, but we face many cases in our industry that we need time urgency, but the current generative AI model just wouldn't work for those cases. But still, like I've only shown one example in the specific case of building element subtype classification. So we are working on broadening up the task into those benchmark data sets that's open, and we are working on it, and that will be also our future work. So I hope to present those in anytime soon. And before I close up, I want to mention that I want to thank the Korean Agency of Infrastructure Technology Advancement and also Institute of Advanced Science Studies in Germany, TUM Germany, for funding the project. And before I close up, I didn't get into detail of what was the task and like how it was evaluated because of limited time and the topic that I wanted to focus. But fortunately, I got one published out like early this year. So if you're interested, like it not only covers the task, but it kind of like covers details of what I presented today too. So with that, I'll finish my presentation and thank you.